Okay, hi everyone. Welcome to tutorial 5. Today we're going to talk about recurrent neural networks. Alright, specifically we're going to cover what RNNs are and how they work. We're going to show a basic implementation, almost from scratch, and kind of similar to previous tutorials, we're going to show one example of an application, which is called sentiment analysis. And then we'll talk briefly about a concept called attention, which is also very popular, specifically with the context of RNNs. Okay, let's go. So first, just a short recap about what we saw so far. We saw models that were composed of either fully connected, which we also called linear layers, or convolutional layers. Two main type of layers that we saw so far. And if you recall, our fully connected layers were defined like this. Specifically in the case of an MLP, each layer transforms the output of the previous layer using a fixed weight matrix that we learn, but it's of a fixed size. And one of the drawbacks was that fully connected layers are completely prefixed in terms of dimensions. You have to decide everything in advance. You have to decide the input dimensions, the output dimensions. So sometimes it's not a problem if you know exactly how many features you have. But for example, we saw that in the case of images, it doesn't necessarily work well. Or it's not what we want, at least. Then we saw convolutional layers, which were a bit different. We saw that what we do, we calculate our output y as a sequence of feature maps, in this case k feature maps, which are convolutions between the full depth of the input and k different filters that we also learn. And this time we share weights, and we're not completely confined in terms of our sizes, because the output shape can change as a function of the input shape. We saw that kind of briefly with fully convolutional layers. So you might have to define some things. For example, if you put a fully connected layer at the end, but the convolutional layers themselves are not so fixed. Okay, but still, one thing that both of these models or layer types cannot model is the concept of state, kind of persistent states. For example, even if you have a convolutional neural network, the output of the network for a given image will not depend on any other image that you previously input into your network. So if I put an image of a cat and then I put an image of a dog, there's no relation. The dog will not be affected by the fact that I put a cat in there before. Okay, so again, it might be useful, but for many tasks, we do want to model kind of a dynamic relationship where the output is a function of either previous outputs or previous inputs or both. Okay, so you can think, for example, if you wanna work with video and you have a convolutional network, and you want to classify what's happening in a scene frame by frame, then it does matter. I mean, the previous frame may change your classification for the current frame. So that's an example where you do kind of need this persistent state to be there. Okay, so recurrent layers are a way to model this kind of relationship. Okay. So just very high level, you can think of it as kind of similar to what we saw in fully connected layers, but we kind of separate between two types of input. So one input is our actual real input, a sample, and the other input is a hidden state from a previous time step. So now we're kind of implicitly saying that our samples have some kind of time order. So we put an index t on them. And we say that we also have a previous state. Now, given these two inputs, our recurrent layer will compute an output for the current time and a new state. Okay, so that's that's very high level. One way to visualize it is like that. Okay, so we have these two inputs here, We have our sample and our previous state, and we create two outputs. Okay, and an important thing to keep in mind is that the function itself is not time dependent. Okay, so you do learn it. It is parameterized, so you do learn it. It does change. The parameters do change over batches and epochs. But if you think about a sequence of xt, like a sequence of different times, it's the same function. Okay, so if I'm running here for a few time steps, I'm computing the exact same function but on different inputs. Okay, so I'm applying the same layer or function successively on multiple sequential time steps of my input. Okay. So more formally, this is how you can define it. You can see kind of the expressions look very similar to what we saw before. So it looks like a activation function operating on some affine transform, like usual, like the FC layers, but we just have two of those, and we're combining here the two inputs. So we have one affine transform for the first input, the x, the sample, and another one for the previous state. This gives us a new state, okay, and then we use this new state using another affine transform and another nonlinearity to compute the output. Okay, and all the dimensions, of course, need to match. Okay. All right. So we can also kind of conceptualize it like that. We can unroll the single time step that we saw, and if we do that, then we see that basically we're just using the same parameters over and over again with different inputs, and it gives us, of course, different outputs and different hidden states. Okay, so you should have seen all that in the lecture. And a crucial issue here is how should backpropagation work? So, anyone remember kind of what the difference is in this case? Well, yes, you have more weight matrices to update. But how do you backprop? Let's say I have all these outputs y, so and I want to update my weights. The best one, or all of them, or the last one. It really depends on the task. But the issue is that I have to backpropagate somehow also through the time steps. It's not enough to just. But I mean, if you think about it, this vertical axis is the layer itself. So this is our feed forward. But we have to backpropagate not just in this direction. We also have to backpropagate in the time direction. Okay, so this is backpropagation through time. It means that we're backpropagating through multiple uses of the same parameter tensor. Okay, so we have to take that into account and accumulate all the gradients because we are reusing these tensors. Okay, and you should have seen it in the lecture, and also there's a truncated version of this kind of thing where you only look to a window, up to a specific window backwards. Okay, so an important and useful property is that their RNNs are very flexible, and you see kind of different relationships in different applications. Okay, for example, I can create a one-to-many relationship. If I'm, for example, doing image captioning, then maybe I want to insert some image features into my RNN and have it generate a sequence of words. Okay, or if I'm doing sentiment analysis, which means classify some sentence as, for example, positive or negative, as we're going to see shortly. So maybe I want to take multiple parts of my sentence, like the words or characters, depends on the model, and create a single prediction based on the input. Okay, or in machine translation tasks, sometimes you have words in one language, and it translates to a different number of words in the other language. Okay, so the fact that you can kind of use any of the outputs that you want, and you can put any inputs in any times that you want, kind of gives you lots of flexibility, and it really depends on your application. What outputs are you looking at, and where you kind of backprop through? Okay, so if you want to kind of make it more general, then you can define a deeper version of the RNN, which is really the same idea. Just you stack another layer, And again, it might be a little confusing, so I just want to, I'm showing this just to kind of emphasize that this vertical axis is what we saw, for example, in the MLP, we call this the depth. Okay, so these are the layers. This direction is more layers, and this direction is something new. Okay? So it's not more layers, it's the same layer because these are the same parameters all the time. Okay, so this layer here has the same parameters, and this layer here has the same parameters. So this is one layer, and this is the other layer. And the horizontal axis is really time and propagating the hidden state so that we can use the sequence of different inputs to generate something new. Okay, so let's try to implement this. Right, so first thing we'll do is just take the equations that we saw and straightforward implement them as a PyTorch model. Okay, so let's define an RNN layer here. So again, I'm calling this a layer because it's one of the blocks that we saw in the previous image. Calling this a layer, we use this block on multiple time steps, but it's still conceptually a layer as layers as we called layers in previous types of models. Okay, so here all I'm doing is I'm defining my dimensions for my inputs x, my hidden dimension, some fixed number, and my output dimension. I have three fully connected layers here. One to transform the input into the hidden state, the other for the previous hidden state to the next hidden state, and one from the hidden state to the output. Okay, so it's really, really basic, straightforward. My forward function now, as opposed to maybe in previous cases, my forward function will now take two parameters, the current input and the previous hidden state. Okay, just for conveniencing, I'm allowing it to be none, so I just zero it in that case. And remember that we're always operating on batches. Okay, you're gonna see it shortly, but here, for example, this is actually a batch of samples, so it kind of makes it a bit more confusing. But my hidden state is also a batch, so I'm taking the batch dimension here and using the number of hidden features that I need. Okay, so the next hidden state is just applying my nonlinearity. Here I parameterized it. I just defined it as a parameter. So this is my activation function. I'm taking my fully connected layer, transforming x into h, and adding another transform from the previous h to the next h. Okay, notice that there's only one bias here in both of these, just to not have an extra bias. Doesn't matter if you do, but okay. And same thing for the y. After I have the new h, I just apply the linear fully connected layer, and if I have I'm allowing my second nonlinearity to be none. So if I have it, I apply it, and that's it. That's the whole RNN layer. Exactly same as it was defined in the equations that you saw in the previous slides. Okay, so let's see if it works. So first of all, I'm just instantiating a model here. We can see all it has are these parameters. 3 fully connected layers. That's it. So let's kind of manually show a few time steps through this model, stepping in. So let's create some input tensor. So I have n is my batch dimension, and I defined some input dimension, which I don't remember what it was. It was 1024. Okay. So I'm just creating a batch of inputs. So this is the batch of inputs that I will feed my model at time step 1. Okay. Batching is a way here to basically just parallelize everything. If I have, for example, multiple sentences, then I can take the first word of each sentence and make a batch from that, and then the second word of each sentence and make a batch from that, and so on. That's what batches mean here. Okay, so all I'm doing here is getting my output for time 1 and hidden state for time 1, and then keep going. I'm just creating a new input and then using the previous hidden state and so on. Okay, and you can see it works. I defined, in this case, an output dimension of 1, but the batch size was 3. Okay, so I'm getting here, I'm getting three numbers out, because it's output dimensions of 1, but I have 3 elements in my batch. Okay, so far very basic. Right, and of course the shapes of the hidden state and the outputs match what we define. Okay, so let's dive into a slightly more interesting example. So let's see how to apply an RNN model to some actual real task. So I kind of searched for something that's small enough in terms of a data set that we can actually show something. And this is an interesting task which talks about classifying sentences which are movie reviews. I think it's taken from IMDb, written by users, and we need to decide whether, based on the text of the review, whether the reviewer thought it was a good movie or negative, or bad movie or neutral, or at least what his stance about the movie is, based on the review. So if the review is best movie ever, we need to find a way to get our network to say it's a positive review. Okay? That's the basic idea in this task. Okay, so the kind of non-deep learning approach was usually to try to, well, you can naively look at keywords. If you have a review if you, for example, look at the words and just say, if the review contains funny and witty, then it's a positive review, then you might fail on this example. And you can kind of intuitively understand that when you read this, you need to maintain some kind of state. You have to know that it says it's neither funny and nor witty. So you have to kind of maintain a state in your head that it's negating the positive words. Okay, so that's kind of the idea of doing that. And specifically, we're going to add an embedding here to our model. And I think what you saw right now in the lecture should give you kind of an intuitive understanding about it. Okay, so let's look at our data. To help ourselves and keep it simple, we're using a package called Torch Text here. It's kind of similar to Torch Vision. It provides lots of useful stuff that I will show. And one of the things that it provides is built-in data sets that it downloads for you, and it's kind of very useful. So I chose a relatively small data set of movie reviews called the Stanford SST data set. Okay, let's look at it. So let's see how we're gonna load and work with the data. So we have this field object its whole purpose is to take text and split it into unique tokens. So tokens are kind of, you can think of it like words, but also punctuation marks are tokens and things like that. If there's an exclamation mark, then it might have some kind of meaning, or a question mark has a meaning. So these are also tokens. So it's not exactly words, but it's similar. So we need something to take our text and convert it into these tokens. And once you have these tokens, you need a numerical representation. You need to convert the text into some tensors that you can put into your model. So there's kind of a pre-processing step here before you can actually take text and do any deep learning with it. So it's useful to see an example of that. So we define here two objects of this field type, which is part of the Torch Text package. Okay, and we're just using some external package for the tokenization, which it can work with. And we're using this datasets module that gives us the SST dataset, downloads it for us in advance. And what this part does is it gives the data from the dataset to our two field objects and populates them. And once it populates them, it creates this tokenization. So it will take all the movie reviews and split them into these tokens. And the same for the labels. So our labels are positive, negative, or neutral. So again, it will take these labels and tokenize them. So let's show you what I mean right now. So just quickly, we have 8,000 examples in our training set. We're not going to train over all of them, only on a small subset. So let's see what we have. So just quickly printing some two samples that I chose at random. You can see that what we have in our data set, in our training data set, objects that have a label and text. So, for example, this is the text of one of the reviews. The film aims to be funny, uplifting, and moving, sometimes all at once. So you can see that this is a positive review, and you can also see the fact that there are spaces here show you that this is also tokens, because I'm joining my tokens with a space. So you can see the punctuation marks are also tokens. And this is a ugly, revolting movie, so it's a negative review. Okay. The next thing we need is a vocabulary, which basically is just a mapping from the token to its unique index, and vice versa. That way we convert our words into numbers, and after that we can use embeddings on them. So this is the next part. The field objects also gives us that ability. It just creates a very simple vocabulary for us. So we can see, for example, that in our text, in the whole corpus of movie reviews, we have 17,200 different tokens. Okay, and in the labels we have 3, because it's just positive, negative, or neutral. Okay, let's see what I mean. So, for example, let's print two things from our text vocabulary. I2S is int to string, so it converts. It's basically, it gives you a list of the first 20 tokens, and the index in this list is their number. Okay, and so you just have a list of all the different unique tokens, and S2I is the reverse. It takes a token and gives you the index. So you can see the word film appears here in the 17th index. So it's the 17th token. And you can notice there are 2 special tokens that were added for us that we didn't specify. So this means unknown. So if you encounter a character that you didn't model in your vocabulary, then you can give it the unknown token, and this is for padding, which you'll see is very useful in a sec. Okay, and in our labels, all we have, I'm just converting my whole S to I to a dictionary, and you can see all we have is just these 3 strings converted into 3 class labels. Okay, so next up, we need some way to load our data into our model. So we have something very similar to the data loaders that we saw. In Torstex, we have iterators. The one issue, though, is that if you want to work with batches, and it means that you're working with batches of sentences, and sentences have different lengths. I mean, reviews have different lengths. So how can you work with batches of these sentences? It's kind of pretty obvious. Padding, right? So that's why we saw the special token padding. When you get a batch of data, you get, for example, 5 sentences. So if they're not the same length, the ones that are shorter will be padded. So the pad token will be added to the end of all these sentences. Okay, let's see an example. So here I define my batch size 4. I create this iterator here using the touchText data module. Okay, and let's take a single batch from that. Okay, so let's see what we got. So I have my data loader. I took the first batch just by iterating once over it, and I split it into the text and the label. So the text now is a tensor that looks like that. Okay, so what does this mean? Why does it look like that? Again, think of batches. Yeah, okay. So you have the first dimension is the length of the sentence, or the longest sentence. Okay, and this dimension is just the batch size. So this is a specific example where the batch size is not the first dimension, and you'll see why it's useful in a second when you see the model, why it kind of makes sense to work like that. Note that if I run it again, I'll get a different shape here. So the sentence length is actually really different each time. Now it's 20. So you see there's one that ends with a different token than 1. And remember that 1, the token in the first index was the padding token. So you can see that all these columns have padding at the end. And 2 is, by the way, 2 is, I think it was a period. Yeah, okay, so this is index 1 and this is index 2. Okay, so you can see that the first batch of sentences that I got here, each sentence is a column. So for example, this ends it with a period and then lots of padding. And this adds with a period, and this ends with a period and then less padding. Okay, so that's what we get. And the Y is just 4 labels. Okay. And yeah, again, note that the sentence length changes every batch. Okay, so it really shows you that we're working with data that has different length each time. So our model needs to take that into account. Okay, so let's now create the model for the sentiment analysis task. Now that we have our data, we have tokenized data, we have a data set and a data loader on top of that. So we'll create a model that will take a batch of these tokenized sentences, which are the columns that I just showed you. We will compute a dense word embedding. So a word embedding, you should have seen it now, is just a vector or a tensor of a fixed size that you specify, and it's not one-hot encoded. It's dense, which means you represent words or tokens in some kind of space. Okay, and there's lots of ways to define it. Then what we're going to do is process the sentence word by word or token by token using our single RNN layer. Okay, we have one RNN layer, and we're just going to process our sentence word by word through that layer. So it's the horizontal direction. And what we will produce is an n by 3. So n is our batch size, and 3 is the number of labels that we have, positive, negative, or neutral. Okay, so we want to input a batch of sentences and get a batch of 3 scores. Okay, because it's a classification task. So we want to have class scores and then do some kind of cross entropy or something on top of that. All right, so let's look at the model. Okay, so this is our RNN for sentiment analysis. We start by defining, first of all, the parts in the model. First of all, we define an embedding. So this is an embedding layer that's built in PyTorch. And you may be wondering what it's doing. Okay, so first of all, what you have to define here is an input dimension and the embedding dimension. So you can, what basically this is doing, it's not any kind of smart embedding or a pre-trained one. It's just a tensor with this number of rows and this number of columns that you can think about it as a lookup table. You give it an index of a token, which is the row in that tensor, and it gives you some random tensor that represents it. From this moment it was initialized, then you have a random embedding for everything. And you can actually train over that, because when you take a word and you get a random vector, it tracks gradients. So if you train this embedding, then you're training your embedding with your model, and you will update the representation for each token. It's not ideal, it's not the best way to train an embedding, but it will do for now. It's one of the limitations of this model. Okay, so after we have that, we use our custom RNN layer, which we built in the previous slide. Right, so now we're working with embeddings. So we define our embedding dimension, our hidden dimension, output dimension, which in our case we want to produce class scores. So we define that we don't want the nonlinearity phi y. We don't want to apply it. So all we will get are 3 class scores, really, not anything that passed through a nonlinearity. And we'll just apply a log softmax on top of that. So we get log probability for each class. Okay, so you can see it in the forward. If you define a forward function taking a tensor here, x. So S here is the sentence length of this specific batch. So remember, the sentence length is the length of the longest sentence in the batch. The others are padded. So you have the longest sentence length and the batch size. You embed it. You compute an embedding, which means for every one of those sentences, now you have a tensor of the embedding dimension. So now you have this. And then now the reason that the batch is not the first dimension in our case is that what we want to do now is we want to go word by word and input every single word as a time step into our layer. That's what we're doing here. We're looping over the first dimension of the embedded tensor. And each time we're getting a batch. Okay, so it's B over E. And we're just providing our network with this batch of words or tokens. Okay, computing the output and the hidden state. We don't need the output actually, most of the time. So we're just computing the hidden state and then passing it on to the next iteration. Finally, after we're done going over all the tokens, we take our last hidden state and log softmax it to get log probability for each class. Okay? Good. Hope it's clear. It's really simple. I mean, it really should showcase kind of exactly what was drawn in the figures that I showed in the beginning. It's really exactly what was drawn. You take your input and split it into time steps and sequentially insert them into your model, propagating the hidden state. That's what's going on here. Okay. Okay. So, but what should our input dimension be? So we didn't. We just define it and put it into embedding. So what should this actually be? If you kind of think about it, what is this doing? Any ideas? Yeah, exactly. The whole corpus length, not length, the number of tokens. Yes, because this embedding it should take those token indices that we saw in our column, okay, and for each one it should create an embedding. So yes, that's what we're defining here. And indeed, the input dimension will be the length of the vocabulary of our training data. Okay, so, and the rest we just define however we want. These are hyperparameters that you need to basically cross-validate. And the output is 3 because we have 3 classes. Okay, so again, let's instantiate our model. Okay, you can see we have an embedding, we have our RNN as before, and we have log softmax. Okay, so this is our sentiment analysis model. Let's see that it works. So we have our X tensor from before. This is the first batch, the columns that we saw. All right. So feeding our batch through the model, we can see that what we got is a tensor of shape 4 by 3. So 4 is the batch size again, and 3 is the number of classes. So these are log probabilities for each class as we want. Okay. So. And these are the labels. Okay, so as usual, we can take these log probabilities, we can do a negative log likelihood, okay, and train like that. Just like training and classify. Okay, so just a quick check. How big is this model? All we had is one RNN layer, which had just 3 fully connected layers that weren't so big. I mean, we just took very modest hidden dimension sizes and things like that. So why do we have 1.7 million parameters here? Where are all the parameters? Sorry? In the embedding, exactly. Parameters are in the embedding. Okay, so again, the embedding here might be a bit confusing because we didn't define anything. We just said, give us an embedding. So it's just a really big tensor that has the number of tokens columns, rows, and the number of columns is our embedding dimension. So it has a lot of parameters. And like I said, each time that you give it a token, it gives you a tensor. That tensor tracks gradients, and then that way, when you train your model, the representation for each token will update. Okay, but again, it's a lot of parameters. All right, so just really quickly show the training. It's exactly the same as with previous models, which is kind of the point here. Even though we're doing really different tasks and we're implementing different models, the kind of same basic training loop is always there. So let's just show it and see that it runs. We have our sentiment RNN model initialized, and we just create some optimizer, and we're using, like I said, the negative log likelihood loss because we have log probabilities. So you can either do that or you can do cross entropy on the class course. It's the same. Okay, so again, basic training loop. We're going over batches from our data loader, getting these column tensors of sentences and labels, passing it through a model, getting predictions, computing the loss using our negative log likelihood, and propagating backward. Okay, so if you remember, what our model is doing, it's feeding it word by word. So we have this horizontal chain of propagating the sentences in the batch. Okay, so this backward will actually do backpropagation through time, because this loss that we got here is a function of the last output, which is also a function of all those time steps. So we're really backpropagating through time. We will update the same tensors multiple times here. Okay, or the gradients will accumulate multiple times, and then we'll do one step to update the parameters. Okay, so just really basically you can calculate the accuracy just by taking the maximal probability, which is the kind of the best prediction, and counting how many correct predictions you have by comparing. Okay, that's it. So if this runs, we have a trainable sentiment analysis model. As you can see, it was pretty short, not a lot of code. I didn't kind of work on the hyperparameters or trying to make it train, because it's also kind of it takes a long time. I'm stopping here after 100 batches or 200 batches, but if you really try to train this thing, then you'll see that even though it's a small model and it's not a huge data set, it's really hard to train without a GPU, especially if you kind of make it deeper. And hopefully you'll see that in the next homework, where you will implement kind of a more complex model, which will be also deeper and more interesting. Okay. So, like I said, there are limitations. This is not really a good model. Is just a very short model and easy to understand model. One of the major problems here is that we're training the embeddings with the model, so it will really make. If you think about it conceptually, it's like two different tasks, and you're starting with completely random embeddings that have no semantic relationships in them whatsoever. So just training that will take a long time. So if you're trying to train that and your actual sentiment analysis task, it might be much harder. So usually we use pre-trained embeddings. And another problem here is that the RNN itself is very naive. We just use 10H activations. If you try to do the forward pass through time, then backward pass through time, then you get the vanishing gradient problems. So we can solve that with gated units and things like that. And also more advanced models for sentiment analysis use kind of bidirectional RNNs, which also look backward and forward. So there's lots of stuff to do, but this is a really basic, short, not a lot of code. And I hope it was clear kind of how to use an RNN to solve a text-related task. Okay, so let's talk about attention just briefly with the time that we have left, the idea behind it, and show a few examples. So the idea behind attention is that when you work with kind of these sequences, or even if you just work with, for example, an image, there may be more salient parts or more important parts in that image or in that sequence. And you want to give them more weight. You want to say to the model, kind of ignore the noise and look at the actual signal. So, and attention is a way to add that capability to your model, and it's also trainable. So you train the model with a capability to kind of know what to focus on. Okay, so that's the basic idea behind it, and the most clear examples that you can give people are from visual contexts. For example, image captioning. So this is a famous paper. I think it was called Show, Attend, and Tell. And you can really see what they're doing. They're creating a caption or a sentence for each image. So this image was captioned, a person is standing on a beach with a surfboard. And they're doing it by, I'll show just the next slide. They're doing it by extracting convolutional features. And they also they do that extraction in a specific way that allows them to map the feature maps back to locations in the image. Okay, and then they use an RNN with an attention model over the image to generate the captions. And what you can see is the correlation between what parts of the image were given higher weight when specific words were generated. So it's hard to read the words here, but for example, you can see the person here on the board is highlighted when the word person is generated. So that's kind of the idea, that you generate some kind of attention over your features, then you input the features with the attention into your RNN, and that way the RNN has a kind of a better idea of what words to generate in this case. That's the idea behind it. So one way to do it is apply some soft attention onto the input. So I think we saw that in the lecture. It was an example in the lecture. This is basically what's going on here. You can see that the input to the RNN is already attentioned. It's already weighted with this model. So I think the most basic way to do it is just like that. You modify your hidden state update. Instead of using the input directly, you gate it. You gate it with kind of an element-wise product here, and use a different transform of the input and hidden state to learn this gating. Okay, so you're learning the way that you should gate the input. Okay, and again, you need to kind of consider that this is constant. This is a constant function of time. So you update it again with batches, but it's the same function for the sequence. Okay. So if you have a sequence, it should learn what parts of the sequence may be more relevant. It's kind of similar to gating that you see inside the networks, like LSTM gating, but it kind of works on the vertical axis, not the horizontal axis, like the LSTM gating. It's kind of similar idea, at least in the input soft attention. And to implement it, like based on what we did, is really straightforward. So you can see that you just can take your pre-existing RNN, just like we did before, add two fully connected layers here, as I just did, and just implement the equations as they are. So it's just calculating the attention part and the gate and the softmax part, which is the gating, and then applying the gate. That's it. Okay. So I can't really show it on the sentiment analysis model because if you think about it, it kind of makes sense to for image captioning, like we saw. If you take the image and you gate it and then you put it in your RNN model, then you should help the model focus. But think about it like think about our sentiment analysis task. How much does it make sense to apply this kind of attention to the inputs? I mean, what will you be actually gating, kind of intuitively? So, in our case, the input to the model are what's really going into the RNN are the embeddings. So if you compute that, then you're basically telling your model to look at some of the dimensions of the embedding more than others for all the words in the sentence. So it kind of doesn't make sense for this task, or it makes less sense. It might make sense if the embedding is really good semantically and you have a specific task where you really might do something with that. But generally, if you think about attention in our context, what you would want to do is tell the model on which words in the sentence to focus. Okay, so if you have the word witty, maybe it's more important than the word the. Okay, in the review. So a different way to do it is to give attention on the features that you generate in your model. Okay, so one paper that you can see from ICLR, kind of recent, was to use what they call self-attention to give attention to the hidden states. So again, intuitively, you have a hidden state per word. After each word, then you have a hidden state. So if you decide what hidden states or what parts of them are more important, then you can kind of make the model focus on more important aspects of the sentence. But the major issue is that since the sentences are of different length, then you have different number of hidden states each time. Okay, so the way they solved it is really simple. They defined something they call the sentence embedding, which is this M matrix. And given all the hidden states that they got from the model, after inputting the whole sentence, they take all the hidden states and concat them together, and apply basically two affine and then nonlinearities to get an attention model, these A's, which they multiply by the hidden states and get an embedding for the whole sentence, which is a fixed size. And once you have that, then it's kind of a weighted sum of these different hidden states, which you can use to classify your sentence. Okay, so it's kind of a deeper kind of embedding. So more formally, the way that they propose to do it here is also very simple. You can take all your hidden states, stack them in a matrix, create this attention over them. Okay, which is, you can think of it intuitively. If you kind of try to unpack this, then it's weighting the different hidden states, and then softmaxing it. So kind of you get a kind of a distribution for each of the states, and then it's combining them into this sentence embedding. Okay, so after you have that, then since your sentence embedding is of a fixed dimension, you can just train a fully connected classifier on top of that, and you have kind of a model that on one hand focuses on the hidden states, but it can do it with different sentence lengths. Okay, so it solves that problem. Okay, and if you go back to our model of for the sentiment analysis, then you can really add these equations to the model by stacking the hidden states and calculating this matrix, add a fully connected layer, and you implemented it. So I'm just giving it as a self-exercise for you guys, if you want to do it. If not, then you'll do something pretty similar, I guess, in the homework. And I think that's it. Yeah, that's it. Thanks.